The nuclear review comes in two parts. There is the brief review here in front of me, and then there's also the extended review. If nuclear chemistry was something that was covered very quickly in your class, then you'd probably want to go to the extended review first, where I develop these ideas with a little more time. All right, natural radioactivity deals with isotopes of the elements whose atomic number is greater than 83. So there's two types of radioactivity, I should say. Natural, which is at the top half of this page, and artificial, which is in the second half. All right. If we're talking about natural radioactivity, we're talking about radioisotopes that spontaneously, which means on their own, decay to give off alpha, beta, or gamma radiation. And the reason why they decay spontaneously is because they have an unstable neutron to proton ratio. So for that reason, radioactivity is also referred to as nuclear disintegration, since the nucleus is made up of neutrons and protons. And this unstable ratio is what makes the nuclei break down and give off these particles and rays. Alpha particles, the Greek letter alpha, consists of two protons and two neutrons packed together. So let's see if we can draw that here. As one particle consisting of four components. That is, two neutrons and two protons. All right, and because of that, alpha particles will have a +2 charge. All right, because only the protons are charged. And together, alpha particles will have a mass of 4 AMUs, since 2 and 2, each weighing 1 AMU, adds up to 4. All right, and in terms of speed, the alpha particles, since they are the heaviest, naturally will be the slowest of the three types of radiation. And as far as keeping yourself protected from alpha particles, you should remember that alpha particles are blocked by a piece of paper, so they have very little penetration, very little ability to penetrate. All right. Beta particles, on the other hand, are electrons, and we use the Greek letter beta with a negative sign, which indicates their charge. All right. Now this is kind of weird, because what we're saying is from the nucleus, electrons are being emitted. And the reason for that is that inside the nucleus, a neutron splits, forming a proton and an electron. And it's the electron that is emitted from the nucleus that we call a beta particle. And it's the proton that remains inside. So you might want to write here that a neutron splits. And then beta particles, since they are electrons, have a -1 charge. They have the mass of an electron, which is 1/1836 or 37 AMUs. And their speed is somewhere in between, faster than alphas but slower than gamma rays. And so because of their small size and their greater speed, they certainly would penetrate paper, but they would be blocked by a piece of metal like aluminum. Gamma rays, on the other hand, are not particles. Gamma rays are a form of light energy. They're, in fact, high-energy X-rays. And gamma rays, being high-energy X-rays, have no charge and no mass. And therefore, they travel at the fastest speed, which is the speed of light. Gamma rays, because of that, are the most penetrating. You would need a piece of lead to stop gamma rays, and therefore they're most dangerous. So let's write that in here. They're the most penetrating. Therefore the most dangerous. So they can ask you all kinds of questions on either the composition of these particles and rays, their charge, their mass, their relative speeds. All right, so this pretty much covers that. Then if you wanted to separate these particles and rays from each other, there's two ways you could do that. You could do it in a magnetic field or an electrical field. And what I have depicted here in the notes is separating them by causing these rays to pass through two charged plates. In fact, this diagram here comes from an old Regents exam. So here we're using electricity to separate radiation. And so let's fill in here. This says a radioactive source. Why don't we just draw a sample of a radioisotope? And it's encased in a block of lead that has a hole inside of it. So the rays are forced to go through that hole to escape. And when they pass between these plates, one being negative and the other, one being positive and the other one negative, you'll notice these plates are electrodes which are hooked up to a battery. So then, because opposites attract, the beta particles are going to be attracted towards the positive plate. The alpha particles will be attracted towards the negative plate. And the gamma rays, because they have no charge, will be undeflected. So again, just emphasizing their charges here: beta negative, alpha positive, and gammas with no charge. Now, if you wanted to separate them another way, you could separate them based on the fact that they have different degrees of penetration. So maybe a diagram here will help you with that. Right? The alpha rays would be stopped by a piece of paper. The beta rays would go through the paper and they would be stopped by a piece of aluminum. And the gamma rays, on the other hand, you would need a piece of lead to stop them, because they would go through the paper, through the aluminum, and be stopped by the lead. So this is separating the emanations here based on the different degrees of penetration. And then what I have up here in the right-hand corner is something called nuclear equations, which are really simple to understand. But again, if you spent very little time on this unit, which unfortunately happens in a lot of classes, this might seem difficult. Let's give it a try anyway. So what I have here are, if you turn to table N, and you're going to need table N and table O to see where this comes from. Let me grab my table here. And so what I have on table N, as it's entitled, selective radioisotopes. And we have here the equations, the nuclear equations of different breakdowns. And the first one at the top of table N is that of gold 198. Notice it says there in table N, the nuclide, or radioisotope, that's breaking down, it says Au-198. The 198 is not the atomic number, but it's the mass number of gold. And if you were to look up gold in your periodic table, in the center there, you'll see that most gold is 196.967. I should say most gold, which that rounds up to 197, is 197, the most common isotope of gold. So a lot of students at first, they give this a double take, because when they come to the periodic table and they round this to 197 and they see a 198 here, they think this is a mistake. But on the contrary, this happens to be in reference to the radioactive isotope, or a radioactive isotope of gold. And so gold 198, we're told here in table N, the gold 198, its decay mode is beta minus. So in other words, the gold will emit a beta particle spontaneously. And when it does that, to depict it, what's going on, we have an equation here that spells it out. So gold 198, you should look up its atomic number here, confirm that, which is number 79, emits, that would be the arrow, a beta particle. Now Now I get this here from this notation from Table O. So if you turn to Table O, on page 6 of your reference tables, you'll see a table there that's entitled Symbols Used in Nuclear Chemistry. All right, if you look up a beta particle under its notation, you can either use E0 -1 or the beta 0 -1. I've chosen to use the E0 here because it reminds me that a beta particle is an electron, but either one will do. And so now to do the math here, and in most examples, what you'll be doing is either figuring out what it decays to or what it's coming from. Let me just show you how to get that. It would be 198, treat the arrow as a negative sign. 198 minus 0 gives you 198. And 79 minus a -1, if you minus a negative gives you a positive, gives you 80. If you look up 80 in the periodic table, you'll find out that that is Hg mercury. So what we're saying is that, in short, this is a natural decay because the gold, this gold isotope on its own does this because of its unstable neutron to proton ratio. On its own, it emits a beta particle, and in the process, it turns into a new element, which is Hg mercury. So natural decay leads to what is called a natural transmutation. Decay is the breakdown of the nucleus. The transmutation is the conversion of one element to another because of this breakdown. All right, let's look at a nuclear equation here for alpha decay. Again, if you turn to table N, the first alpha emitter is francium Fr220. So again, you could look up the atomic number of francium, which is 87. This would be its atomic number. And this isotope of francium, we're told in Table N, emits an alpha particle. So if you turn to Table O, you'll find that this is the common notation for an alpha particle, He42. The reason for that is because the atomic number would give it its symbol. Remember, the elements are arranged by atomic number. And also because an alpha particle consisting of 2 protons and 2 neutrons is a helium nucleus. So then let's do the math again. 220 minus 4 gives you 216. And 87 minus 2 gives you 85. And if you look up 85, you'll see in the periodic table, that is AT astatine. So here I wrote, just check the totals on both sides are equal. In other words, you can do the math here if you'd like. You can see that 220 minus 4 equals 216. If the other one, you could do 87 minus 2 gives you 85. All right, so the totals of the top numbers, which are called mass numbers, the totals of the atomic numbers on both sides should add up, or when you do the subtraction, one should equal to another, since you could treat this arrow as an equal sign also. All right, for positron emission, that would be an E0 with a positive charge. A positron you can think of as a positive electron, and in Table N would be a beta particle with a positive sign. So here, potassium 37, if you look it up in Table N, potassium 37 is a positron emitter. And so anything that I've said about beta particles, the only difference is in the case of positrons is that they have a positive charge, not a negative charge. And the math here again would be 37. All right, here's your positron notation. 37 minus 0 is 37. And 19 minus 1 gives you an 18. So what we're saying is that potassium 37, when it emits a positron, again the mass number remains the same, but it transmutates into argon, an isotope of argon. So we'll practice these in some problems at the end of the unit, And there's, again, more practice of this material in what I call the extended unit on radioactivity. Okay, now let's turn our attention to the center of this page, and we'll look at a topic which a lot of students really do not like, and that is half-life. So if half-life is not your cup of tea, you're not alone. Again, I'll cover this in the extended unit, but in review, let me just remind you that half-life is time. It's time needed to get half the mass that you started with. All right, so it's half the mass. And the half-life of an isotope, you'll notice in Table N, under a half-life, it can really vary from days to minutes to seconds to years. For example, uranium-238 at the bottom of Table N has a half-life of 4.51 10 to the 9th years. That's billion years. All right, so it really varies, but for any particular isotope, it is a constant. It remains the same regardless of what the changes in temperature are, pressure, etc. So it remains the same no matter what you do to an isotope. And in the back of your reference tables, in Table T, you should see these formulas there. That is, total time over half-life time is the number of half-life periods, and the fraction remaining is 1/2 to the T over T, which is what we just mentioned. All right, so just do a typical half-life problem, and if you're stuck, again, you want to refer to the extended unit. All right, so if you're given 100 grams of gold Au-198, which in Table N, if you recall, is at the top of Table N, we're told here that it has a half-life of 2.69 days. What that means is, regardless of what the size of your sample is, every 2.69 days, that sample will be reduced in half. All right? If you recall from your nuclear equation up on top, what's going to happen is that gold 198 is going to, each time a half-life occurs, it'll be forming, as we said a minute ago, let me just refer you up there to remind you, it'll be turning into or transmuting into a beta particle and mercury. So if you start out with 100 grams of gold 198, after the first half-life, you're going to be left with 50 grams of gold 198, and you will have produced 50 grams of mercury. And then after the second half-life, that 50 grams will break down to 25 grams. After the third half-life, you just keep having this. It will chop in half to 12.5 grams, and so on. In this problem here, they ask you, how much remains of this original sample of gold 198, 100 grams, after 10.76 days have passed? Well, you need to find out how many half-life periods fit into those 10.76 days. Those 10.76 days in this case are your total time. And that's always good to circle and label in a problem like this. So this is your total time. And there are only two times involved in any kind of half-life problem. It's either your total time or your half-life time. And when you look up the gold 198, you know that the half-life time is 2.69 days according to Table N. So how many times does 2.69 fit into 10.76 days total? And you get 4. Total time over half-life time is the number of half-life periods. So what I think of it as is there's going to be 4 chops in half of the material you started with. So the 100 becomes 50, which becomes 25, then 12.5, you divide that in half further, and you get 6.25 grams, and that's your answer. Now in the second kind of problem related to half-life, you might be asked, well, what fraction, instead of how much remains, what is your fraction remaining? In that case, it would be the same T over T, which gave you 4 here, but it would be 1/2 to the T over T. And 1/2 to the 4th power is 1/16. Let me remind you how that works. It would be 1/2 times 1/2 times 1/2 times 1/2, and that gives you that, 1/16. So that's another way of being asked this kind of problem, which really what we're saying is 6.25 grams is 1/16 of 100 grams. All right, so we'll do some more problems like this, and particularly in the extended unit. But remember, even if after doing the extended unit you're still jammed up on half-life, it's only one question on the Regents, so try to keep cool over that. And then on the bottom half of this page, we have some notes on the second type of radioactivity, which is artificial radioactivity. Artificial radioactivity, as the name implies, is a man-made thing. All right, you can put a Roman numeral here to remind you that this is artificial and the top half is natural. So man-made in the sense that what scientists do is they bombard the nuclei of elements with subatomic particles, like in this case a neutron. And there are two types of artificial radioactivity. One is fission, which means a splitting, and the second one is fusion, which we'll look at in a second, and that means combining. So why would man want to split uranium-235, which happens to be the most common example of fission? Well, if a slow neutron is shot at a uranium-235 nucleus, and that uranium captures the neutron, it's made unstable, and so it splits, forming 2 smaller nuclei, and from that is emitted at the same time 3 neutrons. So a slow neutron comes in and 3 fast neutrons come out, and let's not forget, energy is also released. So the point of doing this is the energy that's released. A nuclear reaction is a reaction in which mass is converted to energy, in fact, a great amount of energy. And you could use that energy in atomic bombs, or you could use that energy in a nuclear reactor. All right. Here's the equation of this illustration here. The neutron, the N10, which you would find in table O for neutrons, the uranium-235, mass number and atomic number. I got that 92 here from the periodic table. And so combining these two together, and that's what man does, man combines them together so that we end up getting these smaller particles, the splitting, and the 3 neutrons. And you'll notice that the mass numbers, 235 and 1 gives you 236, and 142, 91, and 3 times 1 also gives you 236. Now, if you play back the tape, I said that mass is converted to energy, and so when you first look at this, you might say, well, there's no mass missing. But technically, when you weigh these isotopes to the 3rd and 4th decimal place, you'll find that there is a small amount of mass missing. In fact, that's referred to as the mass defect, and it's that small amount of mass that's converted to a lot of energy in a nuclear reaction. And just as the top numbers add up, you'll see that the bottom numbers do too. The 0 and 92, which gives you 92, will add up to the 56 and the 36, which gives you 92. Remember, the neutron has no atomic number. It's a 0 right there. And there's the key thing, the energy. Now, the energy of an atomic bomb, or the energy involved in a nuclear reactor, isn't just this energy. All right. What happens is that these 3 neutrons continue to split more uranium in something which is called a chain reaction, and that's what I have depicted here. These little explosions here are after the neutrons, the first neutron splits the uranium, and the 3 neutrons are ejected. And those 3 neutrons, then each of these neutrons goes to split more uranium, which splits into smaller particles, and more neutrons that come out and split more uranium, and so on and so on. So in each of these areas here, you should put energy that's released, the energy that's released, more energy, and more energy. So this thing just escalates. It goes faster and faster. And so when you have a lot of energy released in a little amount of time, if it's uncontrolled, that's what a nuclear bomb is about. But if you can control this process by capturing the neutrons, by absorbing the neutrons, and the details of this you really don't need to know, then you could use this energy for good, quote-unquote, good purposes, and then you could use that energy to convert it into electricity. So in a nuclear reactor, the chain reaction is controlled. The problem with fission is the nuclear waste. This barium and krypton is also radioactive, and this nuclear waste happens to have long half-lives, which means it takes a very long time for it to break down, and it lasts a long time. So they have to find a safe place to bury this nuclear waste. The second type of artificial radioactivity is fusion. And fusion is sort of the opposite of fission, because fusion is a combining rather than a splitting of nuclei. All right, fusion is the combining of lighter isotopes to form a heavier isotope. In this example here, you have 2 hydrogen isotopes combining to give you a helium. So 2 and 2 lighter, giving you a heavier 4, and again energy being released. In fact, the energy of fusion is greater than the energy of fission. The energy of fusion is the energy of the sun. On the surface of the sun, this is exactly what's happening. There's the fusion of this hydrogen forming helium and energy. Now you might ask yourself, well, why don't they make fusion reactors or fusion bombs? And the problem is that it takes a lot of energy to get this thing started. So fusion reactions have a high activation energy, which is too high. In both cases, once again, the reason why there's energy being released in the case of fusion and in the case of fission is because in both cases the products weigh less than the reactants. And that missing mass is converted to energy. That's important to note. Mass is converted to energy in accordance with Einstein's equation. The E is the energy, the M the mass, and the C is actually the speed of light squared. The speed of light, you might recall, is 300 million meters per second, which is a very large number. So that's why, although it's a small mass that is missing, that is the defect, that small mass converted by a very large number gives you a tremendous energy outcome. All right, so, and if you compare nuclear reactions to chemical reactions, the energy involved in the nuclear reactions is much greater, because the energy involved in a chemical reaction is due to a difference in potential energies. So chemical reactions are not energy being, as a result of a mass to energy conversion, it's just a difference in potential energy. So nuclear reactions are much more energetic. And finally, at the bottom of this sheet, because radioactivity in review is a very small unit. But again, if you didn't do this in class, you want to do the extended. At the bottom of this sheet, what I call just facts you want to know. You might think of them as random facts, but they're important to know because they typically ask questions about these. And that is the iodine-31, which is used in treating thyroid disorders or diagnosing thyroid disorders, iodine-131 isotopes. Cobalt-60 for cancer treatment. TC99 used for brain tumors. Radioactive dating is when you want to date fossils, or when you want to date rocks, how old they are. You use the carbon-14 to carbon-12 ratio and the lead-206 to uranium-238 ratio. Again, I'm not going to go into this. The coverage is limited for the Regents. You just ought to memorize these things. All right, so just memorize this. Okay, well that's it for radioactivity. What we'll do is we'll do some problems next. And if you're stuck, if I haven't said it enough times, it's got to be annoying, you can go to the extended unit and we'll spend some time developing these ideas, teaching it to you.